Welcome to Management 3120's Chapter 7 lecture. This lecture will cover process strategy, and it's based on the textbook Operations Management, Sustainability and Supply Chain Management, the 12th edition from Jay Heiser, Barry Render, and Chuck Munson. So we're going to get started here. First, we'll cover our learning objectives. So we're going to describe 4 process strategies. We're going to compute crossover points for different processes. We're going to use the tools of process analysis. And then we're going to describe customer interaction in service processes. And we're going to identify recent advances in production technology. So a major decision for an operations manager is finding the best way to produce so as not to waste our planet's resources. So let's look at ways to help managers design a process for achieving this goal. A process strategy is an organization's approach to transforming resources into goods and services. So the objective is to create a process to produce offerings that meet customer requirements within cost and other managerial constraints. So moving on. The objective is to create a process that can produce offerings that meet customer requirements within cost and managerial constraints, which is what we covered in the last slide. However, you also want to know that the process selected will have long-term effect on efficiency and flexibility production, as well as on cost and quality of goods produced. So your process strategies, how to produce a product or provide a service that, number one, meets or exceeds the customer's requirements, meets cost and managerial goals, and has long-term effects on efficiency and production flexibility and costs and quality. So virtually every good or service is made by using some variation of one of 4 process strategies. The first one is process focus. Second one is repetitive focus. The third is product focus. And the fourth being mass customization, which we're going to go over all these here momentarily. Now, within these basic strategies, there are many ways they can be implemented. So the relationship of these 4 strategies to volume and variety is shown here in figure 7.1. So we examined the Arnold Palmer Hospital as an example of a process-focused firm. Also, Harley-Davidson as a repetitive producer, and Frito-Lay as a product-focused operation, and Dell as a mass customizer. So the vast majority of global production is devoted to making low-volume, high-variety products in places called job shops. Such facilities are organized around specific activities or processes. So in a factory, these processes may be accounts payable, sales, and even payroll. In a restaurant, it may be the bar or the grill or maybe even the bakery. And such facilities are process focused in terms of equipment, the layout, and the supervision. So they provide a high degree of product flexibility as products move between the specialized processes, and each process is designed to perform a variety of activities and handle frequent changes. Now, consequently, there are also called intermittent processes, which means they are intermittent. So again, the process focus facilities are organized around specific activities or processes. There's general purpose equipment and skilled personnel involved, a high degree of product flexibility, and typically high costs and low equipment utilization, and product flows may vary considerably, making planning and scheduling a challenge. These slides describe the process focus and illustrate it with Arnold Palmer Hospital as depicted here in figure 7.2a. Now, in general, the product or customer going through a process focused facility has no predefined flow. Any particular product or service may pass through a unique route through the system. Such systems, such as job shops or banks, end up with certain processes having long wait lines while other processes in the facility may be empty. Now, process-focused facilities have high variable costs with extremely low utilization of facilities. Facilities that tend to lend themselves to electronic controls can do somewhat better. Now, referring back here to figure 7.2a, now imagine a diverse group of patients entering Arnold Palmer Hospital, which is a process-focused facility to be routed to a specialized department, and they get treated in a distinct way and then exiting as uniquely cared for individuals. So it was like very specific to what their issue was. Now, repetitive processes use modules, and modules are parts or components previously prepared, often in a product-focused process. And the repetitive process is the classic assembly line, so widely used in the assembly of virtually all automobiles and household appliances. It has more structure and consequently less flexibility than a process-focused facility. So fast food firms are another example of a repetitive process using modules. And this type of production allows more customization than a product-focused facility or modules. For example, meat, cheese, sauce, tomatoes, onions are assembled to get a quasi-custom product, which would be a cheeseburger. In this manner, the firm obtains both the economic advantages of the product-focused model, where many of the modules are prepared, and the custom advantage of the low-volume, high-variety model. So remember, when it comes down to repetitive focus, facilities are often organized as assembly lines. They are characterized by modules with parts and assemblies made previously, and modules may be combined for many output options. And then you have less flexibility than process-focused facilities, but more efficient. And this slide describes the repetitive focus and illustrates it with Harley-Davidson, as figure 7.2b illustrates. A typical assembly line is a repetitive focus, which is a batch flow system. Repetitive processes have some flexibility in creating output variety, but are limited by the variety of sub-assemblies that reach the assembly line. And process-focused facilities have high variable costs with extremely low utilization of facilities. Facilities that lend themselves to electronic controls that could do somewhat better. So just remember, when it comes down to product focus, facilities are organized by product. High volume but low variety of products. Long continuous production runs enable efficient processes. And typically high fixed costs but low variable costs, generally less skilled labor. And this slide describes product focus and illustrates it with Frito-Lay as the example, as seen here in figure 7.2c. Product-focused operations are often continuous flow systems, and they may run 24 hours per day, not stopping for changeovers or for weeks at a time. So product focus is all about creating very high volume in the most efficient way possible. And operations managers use mass customization to product or produce a vast array of goods and services. So mass customization is the rapid, low-cost production of goods and services that fulfill increasingly unique customer desires. But mass customization is not just about variety. It is also about making precisely what the customer wants, when the customer wants it economically. Therefore, it combines the flexibility of a process focus with the efficiency of a product focus. And this slide describes the mass customization as illustrated with the Dell computer model. As this slide suggests, the key to successful implementation of mass customization often rests in designing products and processes that incorporate common subassemblies. So in this way, final customized assembly can occur very quickly to create a unique product, yet the firm does not have to produce and hold every product option in inventory. So this technique is called postponement. In this slide, specifically table 7.1 provides some nice examples of how the number of choices for some products has skyrocketed in the past 30 to 40 years. So mass customization is designed to fulfill those increasingly varying customer needs while still producing large volumes at a reasonable cost. Just going to leave this up here for you to look at. And this slide identifies typical necessary conditions for successful mass customization. Product design must be imaginative. Successful building to order designs include a limited product line and modules. And process design must be flexible and able to accommodate changes in both design and technology. For instance, postponement allows for customization late in the production process. And then you have inventory management requires tight control. So to be successful with build to order, a firm must avoid being stuck with unpopular or obsolete components. And tight schedules that track orders and material from design through delivery are another requirement of mass customization. And responsive partners in the supply chain can yield effective collaboration. Now, these slides replicate Table 7.2 from the textbook, which arguably contains the most important conceptual information in the chapter. It is probably worth spending several minutes covering those comparisons point by point. And characteristics in the repetitive process column typically represent a compromise or intermediate position between the two extremes of process focus and product focus. And to achieve mass customization, the firm would have to ask itself what investments or changes may be required to move from its current strategy in column 1 and 2 or 3 to column 4. Okay? And then I'm just going to leave this up here for you to look at. You can see the differences moving through the process focus, the repetitive focus, and the product focus, and the mass customization. So when you see the process focus, you are dealing with small quantity and large variety of products. In that repetitive focus, long runs, a standardized product for modules. You have the product focus, large quantity and small variety of products. And then you have the mass customization, that's large quantity and large variety of products. And you can see it from organization to organization. Unit costs will be less in the product, continuous or repetitive case when high volume and high utilization exists. However, a low volume differentiated product is likely to be produced more economically under process focus. And mass customization requires exceptional competence in product and process design, scheduling, supply chain and inventory management. Proper evaluation and selection of the process strategies are critical. Now, crossover charts represent the only real math here in Chapter 7. And the examples here in this slide, clever enterprises would like to evaluate 3 accounting software products. So you have A, you have B, and you have C to support changes in its internal accounting processes. The resulting processes will have cost structure similar to those here, shown here in Figure 7.3. The costs of the software for these processes are listed right here in our table. So our approach is to solve for the crossover point for software A and B, and then the crossover point for software B and then C. So moving in with the solution, software A yields a process that is most economical, up to the point in volume, the first point in volume, but exactly what number of reports. So to determine that first point in the volume, we set the cost of software A equal to the cost of software B. So that first point in volume is the unknown volume at this point, and this means that software A is the most economical from 0 reports to 2,857 reports. Okay, now similarly, to determine the crossover point for the second point in volume over time or over production, that we set the cost of software B equal to the cost of software C. And that means that software B is the most economical if the number of reports is between 2,857 and then 6,666. So, and you'll see that on the next slide where, A seemed that it was most economical, but it was at that point in time or at that point in production. And that software C is the most economical if the reports exceed 6,066. So when you can't really just hypothesize based on the first point in production where you're at in volume, that's necessarily going to be the most economically sound approach. So we're going to move on here to the next slide. And as you can see, the software and related process chosen is highly dependent on the forecasted volume. So this slide reproduces Figure 7.3 from the textbook, which illustrates the concepts from the example. And if the fixed and variable costs of different production strategies can be accurately estimated, the crossover charts help to determine the ranges of volume for which each strategy is the cheapest. Okay, and you can see them here, where process A, seemed great from the beginning, but then look how it spikes up over time, or throughout production, and then look at process B, and you can see each respective point, and at what point each process is the most economically sound. So this is like you would integrate this in your strategic vision or your strategic plan. If you're looking for short-term wins, what process to go with. If you're looking for long-term gains, then you would have to use a crossover chart here to see actually which process would be the most economically sound. Now, focusing on processes implies a move towards specialization, limited the number of activities, products, or technologies. So focus is often a reason given why firms outsource so many activities, and the concept of focused processes sounds like the opposite of the goal of mass customization. In fact, it makes you think, which is better to strive for? Is it possible to have focused mass customization? Is it possible to have both? So just remember, focus brings efficiency, focus on depth of product line rather than breadth, and focus can be about the customers, the products, the service, and the technology. Now, It is important to emphasize that the technology decision is not always obvious, and it may involve a large capital expenditure. So ultimately, selection of a particularly process-driven strategy requires decisions about equipment and technology. So these decisions can be very complex, as alternative methods of production are present in virtually all operations functions. And numerous factors may need to be considered, particularly those on this slide, being cost. You have to consider your costs, your cash flow, your market stability, your quality, your capacity, and flexibility. And to make this decision, operations managers develop documentation that indicates capacity, size, tolerances, and maintenance requirements of each option listed here. Now, in addition, equipment that is more accurate or breaks down less often may lead to more stable processes. And this slide emphasized the potential competitive advantage stemming from flexibility. And flexible equipment provides the ability to respond to new orders, make different products with little penalty in time, cost, or customer value. And flexible equipment may allow managers to enlarge the scope of their processes. And since changing processes or equipment can be difficult and very expensive, it is best to get this critical decision right the first time. So remember, flexibility is the ability to respond with little penalty in time, cost, or customer value. It may be a competitive advantage. It may be difficult and expensive. Well, nonetheless, without it, change may mean starting over again. Now, when analyzing and designing processes, we ask questions such as the following. Is the process designed to achieve competitive advantage in terms of differentiation, maybe response, or even low cost? Does the process eliminate steps that do not add value? And does the process maximize customer value as perceived by the customer? So will the process win the orders, is what you're asking. Does the process maximize customer value? Does the process eliminate the steps that do not add value? It's just wasteful at that point. Now remember, process analysis and design not only addresses these issues, but also related operations management issues such as through cost and quality, processes, key, examine the process, then continuously improve the process. And the following tools can, help us understand the complexities of process design and redesign. And they are simply ways of making sense of what happens or what must happen in a process. Now, flowcharts and time function mapping are introduced here. A flowchart is a drawing used to analyze. We know what these are. We've covered them. It's a drawing, in this case, used to analyze movement of people or material. And the difference in between the two being that time function mapping is a flowchart, but with time included on the x-axis. So drawing a flowchart should typically be the first step in any design or analysis effort. Now, the next two slides come from figure 7.4 of the textbook, illustrating that before and after time function map, the time function map used in the process improvement at American National Can Company. So the firm was able to eliminate the significant waiting that had slowed things down before improvement was implemented, as you see here. And in this example, substantial reduction in waiting time and process improvement in order processing contributed to a savings of 46 days in the end. Now, a process chart, like the one here in figure 7.5, breaks down steps into detail and can provide a structured way to examine value-added versus non-value added activities. So essentially, a process chart or charts that use symbols to analyze. They use symbols that analyze the movement of people and or material. And a variation of time function mapping is value stream mapping, VSM. Is the acronym for that. However, value stream mapping takes an expanded look at where value is added and not added in the entire production process, including the supply chain. Now, as with time function mapping, the idea is to start with the customer and understand the production process, but value stream mapping extends the analysis back to suppliers. So again, value stream mapping is a process that helps managers understand how to add value in the flow of material and information through the entire production process. Now, the 9 steps of, to create a value stream map are listed here. So first you begin with the symbols for customer, supplier, and production to ensure the big picture. Then next you're going to enter customer order requirements. Your third is to calculate the daily production requirements, enter the outbound shipping requirements and delivery frequency. And then your fifth step is to determine inbound shipping method and delivery frequency. Your sixth is to add the process steps, i.e. machine and assemble in the sequence left to right. Your seventh is to add communication methods, add their frequency, and show their direction with arrows. And then 8 is to add inventory quantities between every step of the entire flow. 9, you're going to determine total working time, that's value added time, and delay, non-value added time. And in figure 7.6 illustrated on this slide, it displays the value stream map created in example 2 in the textbook. So from this example, we see what looks like a significant amount of inventory as well as a large percentage of non-value added time. And as the textbook suggests, one way to reduce raw materials inventory might be, have to deliveries twice a week instead of once a week. So that's the example you'll see in the textbook. And that would be a way to reduce your raw materials inventory. Of course, if you're going to have deliveries twice a week per once a week. So that's how you would control that mechanism. Now, service blueprinting is a process analysis technique that lends itself to a focus on the customer and the provider's interaction with the customer. So service blueprinting is applicable for processes with a high amount of service content. Your level 1 activities are under the control of the customer. Your level 2 activities represent interactions, and your level 3 activities include activities not visible to the customer. The identification of potential failure points is particularly useful in this case. So again, service blueprinting focuses on the customer and the provider interaction. It defines the 3 levels we just talked about of interaction, and each level has different management issues and identifies potential failure points. Now, the service blueprint shown here in figure 7.7 also notes potential failure points and shows the poka-yoke techniques that can be added to improve quality. Remember quality, we covered quality last chapter, I believe. The consequences of these failure points can be greatly reduced if identified at the design stage when modifications or appropriate poka-yokes can be included, and a time dimension is included here in figure 7.7 to aid understanding, extend the insight, and provide a focus on customer service. Now, interaction with customers often, affects process performance adversely. But a service, by its very nature, implies that some interaction and customization is needed. Recognizing that the customer's unique desires tend to play havoc with the process, the more the manager designs the process to accommodate these special requirements, the more effective and efficient the process will be. Now, the trick is to find the right combination, right? So the 4 quadrants here of figure 7.8 in this slide provides additional insights on how operations managers modify service processes to find the best level of specialization and focus while maintaining the necessary customer interactions and customization. So the 10 operations management decisions that we spoke about in chapters 1 and 2, and we kind of touched on every appropriate chapter thereafter, are used with a different emphasis in each quadrant, which we will expand on more in the next 2 slides. Now, in the upper sections of mass service and professional service, where labor content is high, we expect the manager to focus extensively on human resources, and this is often done with personalized services requiring the high labor involvement and therefore significant personnel selection and training issues. Now, this is particularly true in the professional service quadrant. So remember, your mass service and professional service, labor involvement is high. There's a focus on human resources, and selection and training highly important. And then you have personalized services. Now, the quadrants with low customization tend to be, 1, standardize or restrict some offering as to fast food restaurants. 2, they automate as have airlines with ticket vending machines. Or 3, remove some services such as seat assignments as has Southwest Airlines. So offloading some of the aspects of the service through automation may require innovations in process design, and such is the case with airline ticket vending, your self-checkouts at places like Home Depot, and bank ATMs. So this move to standardization and automation may also require changes in other areas such as added capital expenditure and new operation management skills for the purchase and maintenance of equipment. A reduction in the customization capability will require added strength in other areas. So your service process matrix, service factory and service shop, you have a automation of standardized services, restricted offerings, low labor intensity, responds well to process technology and scheduling, and there's tight control required to maintain the standards. We're going to go back here. Because the customer feedback is lower in these quadrants with low customization, tight control will definitely be required, and I want you to have that as your takeaway point to maintain the quality standards. And also remember, operations with low labor intensity may lend themselves particularly well to innovations in process technology and scheduling. And here in table 7.3, it shows some additional techniques for innovative process design in services. And your managers focus on designing innovative processes that enhance the service. So for instance, supermarket self-service reduces cost while it allows customers to check for specific features they want, such as freshness and color. And think about Dell Computer. It provides another version of self-service by allowing customers to design their own product right on the web. Customers seem to like this, and it's cheaper and faster for Dell. And we're continuing with table 7.3 here, representing the techniques for improving service productivity and including examples of each. You want to go back and spend a little time here? Just leave this up here. You can see how they all correspond with one another. And again. Now, advancements in technology that enhance the production and productivity are changing. And they change how things are designed, made, and serviced around the world. In this section, I'm going to introduce 9 areas of technology. You have your machine technology, you have your automatic identification systems, or your AIS, your process control, your vision systems, your robots, your automated storage and retrieval systems, which are your ASRS, and your automated guide vehicles, your flexible manufacturing systems, your FMS, and the computer integrated manufacturing, the CIM. Now, consider the impact on operations managers. They are combined and linked globally in a seamless chain that can immediately respond to changing consumer demands, supplier dynamics, and producer innovations. So the implications for the world economy and operations management are huge. So we're going to see how all these interconnect or interweave as we move on in these slides. So, much of the world's machinery performs operations by removing material, performing operations such as cutting, drilling, boring, milling. This technology is undergoing tremendous progress in both precision and control. Machinery now turns out metal components that vary less than a micron or 1/76th the width of a human hair. That's pretty accurate. They can accelerate water to 3 times the speed of sound to cut titanium for surgical tools. And such machinery is oftentimes more productive than that of previous generations while being smaller and using less power. And continuing advances in, let's say, like lubricants, for example, now allow the use of water-based lubricants rather than oil-based. Anybody here who works in machinery or tools, power tools, that use lubricants know this. You probably have seen the change involved, where water-based lubricants enhance sustainability by eliminating the hazardous waste and allowing the savings to be easily recovered, and or the shavings, I should say, to be recovered and recycled. You have your computer intelligence. It often controls this new machinery that I was talking about, right? Allowing more complex and precise items to be made faster. And such machinery with its own computer and memory is referred to as having, computer numerical controls. Those are electronic controls, and they increase the speed by cutting changeover time. They also reduce waste because the fewer mistakes and enhancing the flexibility. So, this slide identifies the improvements that modern machine technology has introduced, especially when computer numerical control, or CNC, machines are employed. Now, automatic identification systems. You should all be pretty much familiar with this. The AIS is a system for transforming data into electronic form. So the AIS applications described in this slide refer to such things such as barcodes and radio frequency identification, which is the RFID acronym. And it's a wireless system in which it integrates circuits with antennas and send radio waves. So essentially anything that eliminates manual data entry. So barcodes allow warehouses to automatically sort hundreds of boxes per minute, and they significantly speed up the checkout process at retail stores, even allowing for the self-checkout stations that are becoming more and more prevalent. The RFID has unlimited potential. As the illustration here on this slide implies, the RFID may someday allow the customers to have all items in their cart totaled in an instant without any physical handling of the products. Like you won't have to put it on a belt or scan manually. It could also act as an effective security device against shoplifting. Now this slide, describes process control, which automatically monitors output signaling when a discrepancy exists, and process control of information technology to monitor and control a physical process. So, for instance, process control is used to measure the moisture content and thickness of paper as it travels over a paper machine at thousands of feet per minute. And process control is also used to determine and control temperatures, pressures, and quantities in petroleum refineries, petrochemical processes, cement plants, steel mills, nuclear reactors, and other product-focused facilities. Now, process control systems operate in a number of ways, but the following are your typical ways. So you have sensors collect data, which is read on some periodic basis, perhaps once a minute or even per second. Measurements are translated into digital signals, which are transmitted to a computer. And you have computer programs read the file and analyze the data. And then the resulting output may take numerous forms. And these include messages on computer consoles or printers, signals to motors to change value settings, warning lights or horns, or statistical process control charts. Now, vision systems combine video cameras and computer technology and are often used in inspection roles. So visual inspection is an important task in most food processing and manufacturing operations. Moreover, in any applications, visual inspection performed by humans is very tedious, mind-numbing, and error-prone. So thus, the vision systems are widely used when the items being inspected are very similar. So, for instance, here, vision systems are used to inspect Frito-Lay's potato chips so that imperfection can be identified as the chips proceed down the production line. The systems are used also to ensure that sealant is present and in proper amount on Whirlpool washer machines, the transmissions, vision systems are consistently accurate. They do not come bored and are of modest cost. So think about the savings, and you learned about productivity, especially in multi-factor productivity, all the variables at play in the inputs and how you can have, even if you have the same amount of outputs, if you're working with less inputs, you're being more productive. So I want you to correlate that concept here with what we just learned about vision systems, and think about how much money it probably costs to pay individuals' salary to inspect these potato chips in the past, and now with the modest costs, how that money just kind of transitions. Number one, you would have to take that factor out of your, it would no longer be a variable or a factor in the equation, so it would be less inputs in for your productive outputs. So just remember, these systems are vastly superior, to the individuals that were trying to perform these tasks. Not only was it more costly, but way more accuracy, because you take a lot of the subjectivity out of it. Now, when a machine is flexible and has the ability to hold, move, and perhaps grab items, we tend to use the word robot. Robots are mechanical devices that use electronic impulses to activate motors and switches. Robots may be used effectively to perform tasks. Just going to put you on hold here a minute. And I'm back. Sorry about that. Had a knock at the door. The automobile industry, for example, they use robots to do virtually all welding and painting on automobiles. And a new, more sophisticated generation of robots are fitted with sensors and cameras that provide enough dexterity to assemble, test, and pack small parts. Remember, robots may be used effectively to perform tasks that are especially monotonous or dangerous, or those that can be improved by the substitution of mechanical for human effort. And such is the case with consistency, accuracy, speed, strength, or power can be enhanced by substitution of machines for people. Okay. So robots are your mechanical devices that use electronic impulses to activate motors and switches. Robots may be used effectively to perform tasks that are especially monotonous or dangerous, or those that can be improved by the substitution of the mechanical for the human effort. That's what you want to remember. Now, because of the tremendous labor involved in error-prone warehousing, computer-controlled warehouses have been developed, and these systems, known as Automated Storage and Retrieval Systems, ASRS, provide for the automatic placement and withdrawal of parts and products into and from designated places in a warehouse. And such systems are commonly used in distribution facilities of retailers such as Walmart, Tupperware, and Benetton. These systems are also found in inventory and test areas of manufacturing firms. And your automated material handling can take the form of monorails, conveyors, robots, or automated guided vehicles. Your automated guided vehicles, or your AGV is the acronym, are electronically guided and controlled carts used in manufacturing and warehousing to move parts and equipment. They are also used in agriculture to distribute feed, in offices to move mail, and in hospitals and jails to deliver supplies and meals. Now, when a central computer provides instructions to each workstation and to the material handling equipment such as robots, your ASRs, and your AGVs, as just noted, the system is known as an automated work cell, or more commonly, a flexible manufacturing system. And FMS is the acronym. And FMS is flexible because both the material handling devices and the machines themselves are controlled by easily changed electronic signals, or computer programs. And operators simply load new programs as necessary to produce different products. And the result is a system that can economically produce low volume but high variety. For example, the Lockheed Martin facility near Dallas efficiently builds one-of-a-kind spare parts for military aircraft, and the costs associated with changeover and low utilization have been reduced substantially. Flexible manufacturing systems bridge the gap between product-focused and process-focused facilities. Now, flexible manufacturing systems can be extended backward electronically into the engineering and inventory control departments and forward to warehousing and shipping departments. So in this way, computer-aided design, or CAD, generates the necessary electronic instructions to run a numerically controlled machine. And in a computer integrated manufacturing environment, a design change initiated at a CAD terminal can result in that change being made in the part produced on the in a matter of minutes. So when this capability is integrated with inventory control, warehousing, and shipping as part of a flexible manufacturing system, the entire system is called a computer integrated manufacturing, or the acronym is known as a CIM. Now, this slide, specifically figure 7.9 here, provides a nice example of the possibilities of a computer integrated manufacturing, or a CIM. Now remember, the computer integrated manufacturing includes computer aided manufacturing, your CAM, your flexible manufacturing systems, your FMS, and your automated storage and retrieval systems, your ASRS, and your automated guided vehicles, your AGVS, and your robots, to provide an integrated and flexible manufacturing process. Now follow the arrows on this slide and you can see the interweaving of each respective process. Your CAD designs the product and programs the automated production, and your CAM converts raw materials into components or products. Your ASRS then and your AGVs then move incoming materials and parts, work in process, and complete your products. Your robots and specialized equipment will and they insert and assemble your components, and your robots will also test, they'll package and ship the finished product. And they do all this, if you see over to the top right there, they do it with an integration of operations management efforts, wherein the operations manager or managers run the production process, purchasing components, coordinating suppliers, planning and scheduling operations, overseeing the quality and the workforce, and shipping to the customers. And these slides reproduce table 7.4 from the textbook. Here we see several examples of technology literally changing the way that service processes operate and the way in which customers obtain services. So in some cases, such as online news outlets versus physical newspapers, traditional service offerings have become endangered. And in other cases, such as ability to pre-order lunch at the 9th tee box on the golf course, technology may have opened new markets. Instructors can spend a fair amount of time, as instructors are supposed to spend a fair amount of time on these two slides. Even with brainstorming, students, you may start brainstorming what's going to be coming next, So just like look at these slides and, do a little forward thinking and some brainstorming. For example, what else can be crammed into the next smartphone? And when you look at this slide and you're looking at the next, even right now, using technology, instructional technology, through Screencast-O-Matic, and this lecture is going to be uploaded on Blackboard, and you see right there in education how learning management systems and like Blackboard have emerged, and some of you can even watch this lecture right on your smartphone. And just as we've seen rapid advances in technology in the manufacturing section, we've all seen dramatic changes in the service sector. These range from electronic diagnostic equipment at auto repair shops to blood urine testing equipment at hospitals, also to retinal security scanners at airports. This table provides a glimpse of the impact of technology on services. Operations managers in services, as in manufacturing, must be able to evaluate the impact of technology on their firm, and this ability requires a particular skill when evaluating reliability, investment analysis, human resource requirements, and maintenance services. Now, A few years ago, the hot catchphrase for a process redesign was business process reengineering. Whatever the term, every once in a while, a process should be re-examined to see if it remains the appropriate vehicle for producing the product or providing the service. Now, such examination may be spurred by new products or product mixes, changes in competitive priorities of the company, changes in volume of demand, poor performance, new technology, changes in the cost or availability of inputs, or perhaps new legislation or regulation. So as humans seem to get attached to familiar process redesign is often easier said than done. So sometimes a consultant or other objective set of eyes may be needed to break down certain processes to bring about dramatic improvements in performance. So remember, process redesign is the fundamental rethinking of business processes to bring about dramatic improvements in performance. Now, this concludes the Chapter 7 lecture. Please check all the expectations and deliverables associated with this chapter, and I will see you in Chapter